Hi students, now this is the third lecture on geometrical isomerism. Now in this class we are going to calculate total number of geometrical isomers according to the given molecule. Okay, so directly I am going to write the general formula which is used for the calculation of number of geometrical isomers, right? First one I am going to take calculation of number of geometrical isomers. Actually here we have two cases. I am taking like this case 1 in the calculation of total number of geometrical isomers. What is the case 1? Now first case, if given molecule is if molecule is unsymmetrical, what is the formula? If molecule is unsymmetrical, then what is the formula? Okay, if your molecule is unsymmetrical molecule, then number of geometrical isomers calculated by number of Gi equals to 2 to the power of n. Okay, very simple. If your molecule is unsymmetrical, so we can easily find out whether the given molecule is symmetrical molecule or unsymmetrical molecule. That is not about problem, right? So now if your molecule is unsymmetrical molecule, directly we can apply number of geometrical isomers equals to 2 to the power of n. Here what is the n value? That n value is very important. Clearly I am writing like this, where n equals to what? N equals to number of one second, n equals to number of stereogenic centers, but not simple stereo centers. There is a difference between stereo center and stereogenic center that we will discuss in optical isomerism. Right now just you remember this formula, right? If molecule is unsymmetrical, then what is the formula to calculate the total number of geometrical isomers? 2 to the power of n. And what is the n value? Number of stereogenic centers. Or another important point, number of segments which are responsible for geometrical isomerism. Gi nothing but geometrical isomerism. That is the case 1 situation, right? So once again we have two different cases. First case, if the given molecule is unsymmetrical molecule, and second case, if given molecule is symmetrical molecule, right? So if your molecule is unsymmetrical molecule, how we are calculating total number of geometrical isomers? Total number of geometrical isomers equals to 2 to the power of n. Here what is the n value? N value indicating that number of stereogenic centers. So whatever the stereogenic centers are, we can take like this: stereogenic area, number of stereogenic centers or stereogenic area. Okay, that's the n value. Next one are number of segments which are responsible for geometrical isomerism. Okay, so where you are producing geometrical isomerism, for example one particular area is there or one stereogenic center is there, with respect to that, so if you are producing what geometrical isomers, then you can take it in terms of what n value, right? This is the case 1. And what is the case 2? Come to case 2. Second case, okay, if molecule is symmetrical, then what is the situation? Here two cases are there. For example, number of segments even or number of segments are odd. Okay, first case, if number equals to even, number of segments equals to even, or n value equals to odd. These are the two different cases if your molecule is a symmetrical molecule. Okay, so if n equals to even, then what is the formula? N equals to odd, then what is the formula, right? Here also same thing, n value is number of segments which are responsible for geometrical isomerism. Okay, right? So here formula, number of geometrical isomers equals to 2 to the power of n minus 1 plus 2 to the power of n minus 2 by 2. Just to remember this point, if it is even, here you will find even number. Okay, 2. Next one here, number of geometrical isomers equals to, number of geometrical isomers equals to 2 to the power of n minus 1 plus 2 to the power of n minus 1 by 2. If it is odd number, here you will find odd number 1. Okay. These are the two formulas if your molecule is symmetrical molecule. Once again, if your molecule is unsymmetrical molecule, no confusion, only one formula directly, number of geometrical isomers equals to 2 to the power of n, right? And if your molecule is symmetrical, you have two options, that n equals to even number or n equals to odd number. Number of stereogenic centers are even, then this is the formula, and number of stereogenic centers are odd, then this is the formula. Okay, so on the basis of these formulas, how we are calculating geometrical isomers, total number of geometrical isomers. But sometimes here we are unable to apply formula in few molecules, especially in case of what cyclic compounds. By applying some logical approach, so we can write the geometrical isomers. That's not a word problem. First let me complete. Okay, so whatever the molecules which requires these formulas. Now first example I am writing, first question, like CH3, next one CH double bond CH, next one CH double bond CH and C2H5. First I am giving unsymmetrical molecule. Is it possible to divide that molecule into two equal parts? Not possible. What is the reason? Left side here methyl group is given and right side ethyl group is there. Okay. Even the two double bonds are what present for geometrical isomerism. First we are trying to divide that molecule into two equal parts. If you are able to divide that molecule into two equal parts, then your molecule is symmetrical molecule. Okay. And if you are unable to divide that molecule into two equal parts, that molecule is unsymmetrical molecule. Very simple. Okay. We don't need any much more symmetry operations and symmetry elements. Whatever the molecule given in geometrical isomerism, first you look at the molecule, right? And just you try to divide that molecule into two equal parts. If it is divided, molecule is symmetrical, otherwise unsymmetrical. Now is it possible to divide that molecule into two equal parts? No chance. Why? Because left and right side groups are what? Different, right? So now this is unsymmetrical molecule. Given molecule is unsymmetrical molecule. Okay, then what is the formula to calculate geometrical isomers? Geometrical isomers, first one, we have two double bond segments, two segments are there. On the basis of substitution, first we are trying to check now these double bonds will show geometrical isomerism or not. Okay, now come to this one. Now this double bond segment, this double bond can show geometrical isomerism. Why? Because already few examples are completed in the last class. On the basis of that, now directly we can say that which is responsible for geometrical isomerism. Here on this carbon atom, hydrogen and methyl, yes, they are different. Hydrogen and this entire group, they are different. So now out of two double bonds, there is no problem with this double bond. It can exhibit geometrical isomerism. And come to this one, this molecule, this double bond also shows geometrical isomerism. Totally we have how many segments in the given molecule? We have two segments in the given molecule. That's why number of geometrical isomers equals to, what is the formula? First your molecule is symmetrical molecule or unsymmetrical molecule. Your molecule is unsymmetrical molecule. Directly apply this 2 to the power of n. What is the n value here? N value 2, that is equals to 4. That is a way of calculating total number of geometrical isomers. Clear? Fine. Come to next example. Yeah, next question. Here I am taking like this carboxylic acid COOH and then here CH double bond CH double bond CH. Okay, and further they are giving like this CH2. Okay, no problem. And further extension given like this CH double bond NOH. Whatever the lengthy molecule is given. Okay, now size of the molecule is not the problem. Just you try to identify number of segments which are responsible for geometrical isomerism. That's enough. Whatever the number of segments they can give, no problem. Now this is our molecule. First I am looking for number of segments which are responsible for geometrical isomerism. Clear? Here first I am starting from this double bond. Now is it possible to produce geometrical isomers with the help of that double bond? Yes, all conditions are satisfied. Again I am not going to take every time these are the different groups, and this can show geometrical isomerism. I don't want to go again and again. Yes, this double bond can show geometrical isomerism. This is my first segment. Okay, that's my first segment which is responsible for geometrical isomerism. And come to second double bond. Now second double bond also shows geometrical isomerism. All conditions are perfectly satisfied. And come to this one. Now oxime is given. This oxime also shows geometrical isomerism. First of all, your molecule is symmetrical molecule or unsymmetrical molecule. No doubt your molecule is unsymmetrical molecule. Okay, no confusion. Directly we can apply this formula. Number of geometrical isomers equals to, what is the formula? Very simple formula, 2 to the power of n. And what is the n value here? Number of segments or number of stereogenic centers which are responsible for geometrical isomerism. Okay, sometimes what is the mistake we are doing? Now they are taking two centers. Stereogenic center means this one and this one. That is not correct. There is a little difference between stereo center and stereogenic center, right? That we will discuss very clearly in optical isomerism. Right now just you remember like this, which is responsible for geometrical isomerism. Either you can take stereogenic center or stereogenic area. This one completely taken as stereogenic center. Okay, don't go for individual carbon atoms. That double bond is responsible for geometrical isomerism. Clear? So that is responsible for geometrical isomerism. That's why with the help of that double bond or about the double bond, you can produce geometrical isomers. That's why what we are taking, stereogenic center or stereogenic area. Totally we have 3, 2 power 3. Total how many number of geometrical isomers? 8 geometrical isomers. Clear? Okay. Come to next example. I am going to take combination of double bonds and rings. Or now for example, if you take this molecule CH double bond CH, clear. Next one CH double bond CH, again right hand side 3-member ring system is given. So what we observe in this molecule, first directly don't apply any formula. First you try to identify the given molecule is symmetrical molecule or unsymmetrical molecule. Yes, according to the given molecule, first I am trying to divide this molecule into 2 equal parts. Okay, for example, if I am taking one particular or plane, okay, just like I am taking what plane, otherwise simply from here I can separate this molecule into 2 equal parts, plane of symmetry, axis of symmetry. These things we will see in optical isomerism. Now is it possible to separate now this molecule into 2 equal parts? Yes, you can separate. Why? Because symmetrical molecule is given. You can divide this molecule into 2 equal parts. And after that, yes, it is confirmed our given molecule is symmetrical molecule. Clear? Then you go for what are the segments which are responsible for geometrical isomerism. Now 2 double bonds are there. Is it possible to produce geometrical isomerism about this double bond? Yes, that double bond can exhibit geometrical isomerism. And this double bond also shows geometrical isomerism. Now we have how many segments for geometrical isomerism? We have 2 segments for geometrical isomerism. Clear? So now 2 segments are there. But what is the formula? If n value is even, here I am taking like this. What is the n value? N value is even. And what is the nature of your molecule? Symmetrical molecule or unsymmetrical molecule? Your molecule is symmetrical molecule. Then how to apply formula? Number of geometrical isomers equals to, number of geometrical isomers equals to 2 to the power of n minus 1 plus 2 to the power of n minus 1 by 2. Is it correct? No. Because of giving even segments here what you are getting? N minus 2. Okay, right. 2 to the power of 2 minus 1 plus 2 to the power of 2 minus 2 by 2. Okay, right. So 2 to the power of 1 means 2 plus 2 power 0 means 1. What are the total number of geometrical isomers? 3. So that is the way of applying formula, right? Yeah, come to next example. I am going to take one more example like this. Here, one second. In the previous example, what we did, one second, carboxylic acid, CH2. Yeah, no problem. This is unsymmetrical molecule. Next one, I am taking like this. Yes, COOH. Next one, CH double bond CH, CH double bond CH, CH double bond CH, and COOH. This is the given molecule. Yeah. calculate total number of geometrical isomers. Again, what is the procedure? For every molecule, now you follow same procedure. First one, our molecule is symmetrical molecule or unsymmetrical molecule. Now tell me this point, symmetrical or unsymmetrical? Yeah, just you look at the groups left extreme left and extreme right side, and three double bonds are what given. Is it possible to divide this molecule into two equal parts? Yes, I can divide. Okay, so your molecule is symmetrical molecule. Yes, your molecule is symmetrical molecule. Very clear. Fine. Next, what are the segments? Identify segments. Now this is my first segment for geometrical isomerism, second segment for geometrical isomerism, and this is my third segment for geometrical isomerism. Clear? Now three segments are there. That means what is the n value? Even number or odd number? Odd number. Then how to apply formula? Number of geometrical isomers equals to. How we are applying that formula? 2 to the power of n minus 1 plus 2 to the power of n minus 1 by 2. What are the number of segments? 3. 3 minus 1 plus 2 to the power of 3 minus 1 by 2. 2 square, 2 square plus 2 power 2 by 2. These two gets cancelled, right? Then 2 square, 4 plus 2. Total how many number of geometrical isomers? 6. Once you check calculation, 2 square plus 2 to the power of 2, 3 minus 1, 2 by 2, 2 gets cancelled, 2. Okay, no problem. These are the total number of geometrical isomers for a given molecule. So that is a way of applying formula according to the given molecule. Sometimes our molecules are symmetrical, sometimes our molecules are unsymmetrical. On the basis of that, we are applying that formula, right? And one more example, pH, CH double bond, CH. Next I am giving 6-member ring system, right? Double bond is there. Next further continuation here. Now CH double bond NOH. Calculate total number of geometrical isomers. First you tell me this point. According to that given molecule, your molecule is symmetrical or unsymmetrical? Yeah, just by looking at that we can say that our molecule is unsymmetrical. Where you can divide that molecule? Not possible, right? So given molecule is unsymmetrical molecule, not possible to divide into two equal parts. Unsymmetrical molecule. Yes, clear. If molecule is unsymmetrical, no problem. Directly we can apply that formula. Number of geometrical isomers equals to 2 to the power of n. Clear. But here what is the next important task? Next important task is identify total number of segments which are responsible for geometrical isomerism, right? So here there is no doubt at all about this double bond. This is my one of the segment for geometrical isomerism. Here also no problem, oxime system, right? Now come to this point. Before going to select another segment, now just you tell me this point. I have 6-member ring system and a double bond also. Here I am giving something like any groups, anything, A, B, B, whatever it may be. Okay, let A and A. Now this molecule shows geometrical isomerism or not. First point. Already we know that up to 7-member ring system, double bond will not show geometrical isomerism. Cyclopropene, cyclobutene, pentene, hexene and cycloheptene. Up to 7-member ring system, okay, if there is a double bond inside the ring system, about the double bond we cannot produce geometrical isomers, right? That's why I am going to neglect this double bond. Don't think about geometrical isomerism about this double bond. Clear? Now come to next one. We have here sp3 carbon atoms. Okay, whatever the substitution given, irrespective of the given substitution, by default here there is a hydrogen and hydrogen. Here and here same or different? They are different. Hydrogen and A same or different? They are different. That's why now this particular segment, otherwise I use this yellow color. Yeah, this particular segment is responsible for geometrical isomerism. Okay, combination of these two carbon atoms is considered as one segment that is responsible for geometrical isomerism. Way of applying formula is very important. For example, in place of this one, if you are taking n value equals to 2, then you are going to do wrong. That is very important, right? Here no geometrical isomerism about the double bond, but in the ring system there is a segment. What is a segment? Let it is hydrogen. Next one, here also hydrogen. Okay, this particular area which contains two carbon atoms, that total segment is considered as responsible for geometrical isomerism. So totally here how many segments are there? Now there are three segments for geometrical isomerism, right? This is the first segment and this is the second segment, but not the double bond. Ring carbon atoms, that combination of two carbons considered as one segment. Next one here, third segment, and your molecule is unsymmetrical. Then what is the formula? 2 to the power of n. 2 power 3 equals to 8. Okay, these are the number of geometrical isomers. Yeah, clear. Come to next example. This kind of example very important, right? Here phenyl is given. Next one, CH double bond CH. Further here 8-member ring system given. Very important question. Yes, there is a double bond and further connectivity. This is the 8-member ring system. Further connectivity is given like this: CH double bond CH and further CH double bond NOH. That is the given molecule. Calculate total number of geometrical isomers. Very important question. Yeah, first we are looking for symmetrical or unsymmetrical. Now your molecule is unsymmetrical molecule, right? And we are looking for number of segments which are responsible for geometrical isomerism. First I am taking this one. I have no confusion about the double bond. Yes. And second segment, third segment. Okay. In these three segments, there is no doubt at all they can show geometrical isomerism. And come to the ring system. Here selection of segments very important. First point, here if double bond is part of the ring system, double bond is part of the 8-member ring system, cyclooctane. Already we discussed in the previous lecture. In cyclooctane, right, we have two isomers, cis cyclooctane and trans cyclooctane. Okay, if double bond is part of the 8-member ring system, that double bond can show geometrical isomerism. That's why you can consider this is also one segment for geometrical isomerism. Next one, in addition to that double bond, one more segment also there. What is the segment? Combination of these two carbon atoms. Combination of these two carbon atoms. That combination can also show geometrical isomerism. Ring system. Totally we have how many segments? 5 segments are there. 1, 2, 3, 4 and 5. Number of GI equals to, what is the formula? Totally we have how many segments? We have 5 segments. Yes, 2 to the power of 5. What is the answer? 32. Total number of geometrical isomers, 32 geometrical isomers. Clear? This is the way of applying formula in symmetrical molecules and unsymmetrical molecules. Clear? Next one, what about calculation of geometrical isomers in cyclic systems? First I am going to discuss about decalene molecule. This is very important. Decalene. What is the structure of decalene? Not complicated, very simple. Yes, decalene molecule. Yes. So this is our decalene molecule, combination of two 6-member rings. Clear? Yes, here also 6-member ring system. That is our decalene molecule, right? At fused position there are hydrogen atoms, hydrogen and again hydrogen. How we are producing cis-trans isomers? Now let me explain, right? So I am going to take that 6-member ring once again. Yes, this is our 6-member ring systems combination. Here also I am writing like this, combination of two 6-member rings. Next, at fused position, sometimes they are giving like this, hydrogen atoms. Above the plane, hydrogen. Again here also, above the plane, hydrogen. Clear? Above the plane, hydrogen. Here one hydrogen atom above the plane and one hydrogen atom below the plane. These are the two possibilities. At the junction of these two rings, now this is the fused position, two hydrogen atoms are there. According to the arrangement of these two hydrogen atoms, we can produce geometrical isomers. For example, if both are present in same side, both are present in same side, what is name of this isomer? We call it as cis. Both hydrogen atoms are present in same side and this one is taken as cis. Now this is the cis form. Here one is above the plane and one is below the plane. So what is the form? Now this is trans form. Okay. One is cis and one is trans. So in general stability point of view, trans is more stable than cis. So clearly we will discuss in conformational analysis. No problem. Just here my topic of discussion is only geometrical isomerism. Cis and trans. These are the two geometrical isomers. Now for the given molecule. Here how to write this molecule into non-planar form. Very simple. I am going to take one more page for clear representation. Yes, this is our molecule, decalene molecule. Okay, and in first one we are taking hydrogen atoms at the junction of these two hydrogen above the plane. What happened? Okay, next one hydrogen above the plane. Now this is cis or trans, cis form. Cis form. Okay, right. And how we are converting that molecule into non-planar form. Generally, what is a stable form of cyclohexane? Stable form of cyclohexane is chair form. We have lot of conformations of that six-member ring system, but among the different conformations, chair form is the more stable form. First, I am going to take right side ring system. Just I am taking like this A and B ring. First, I am taking ring A. Now, six-member ring system like this, chair form. This is the way of writing chair form. Someone writing like this, now this is not the correct representation. I will tell you clearly in conformational analysis. This is the wrong representation. This is not correct. This is the correct representation for chair form. Okay, fine. Yeah, after writing that chair form, next go for hydrogen atoms. How these hydrogen atoms are arranged? Above the plane or below the plane? Above the plane. Now this is the ring A. Hydrogen atoms above the plane. Now in non-planar form, simply you write like this, hydrogen above the plane. And here at this carbon atom, hydrogen above the plane or below the plane? Again above the plane. Okay. Again there is a difference like axial bonds and equatorial bonds. So clearly we will see in case of conformational analysis, no problem. After writing these two hydrogen atoms, again come back to carbon atoms. For example, if this hydrogen atom is above, then what is carbon? Below. And this hydrogen is above, then what about the carbon? Below. Now this is the representation of cis decalene molecule. So once again, hydrogen above the plane, here also hydrogen above the plane, hydrogen above the plane, hydrogen above the plane. If hydrogen atom is above the plane, then your carbon should be below the plane. Next one, here also carbon should be below the plane. So we want how many carbon atoms in ring B? We want 6 carbon atoms. That's why we are taking 6 carbons. 1, 2, 3, 4, 5, 6. Clear? Okay. Next one, I'm going to write trans-decalene molecule, right? This is my trans-decalene. Again, combination of two 6-membered rings. Trans-decalene nothing but what about stereochemistry of two hydrogen atoms, same side or opposite side? Now these two hydrogen atoms should be in opposite direction. One hydrogen atom we are taking above the plane and one hydrogen atom below the plane, right? According to wedge representation. Next one I am taking like this. This is ring A and ring B. Okay. How to convert that molecule into chair form? Yes, first I am going to take A. Now this is my ring A, chair form, like this. Okay, fine. Next one, what is hydrogen atom? One hydrogen atom below the plane. one second, yeah, hydrogen below the plane. Clear? And what about this hydrogen atom? Above the plane. Just you write above the plane. If it is upside, above the plane, downside, below the plane. That's it. Next, what about ring B? How to write ring B? Now this is the ring B. Yeah. This is our ring A and ring B. Now this is the geometrical isomerism in decalene molecule. Now once again come back to same example. Okay, cis decalene and trans decalene. Now stability point of view, trans decalene is stable than cis decalene. Reason I will explain in conformational analysis. Now this is the way of writing cis decalene molecule. Next one, trans decalene molecule. Okay, clear. Next one, come to next important examples when the cyclic compounds are what given like this. For example, 3-member ring system is given. Simply they are giving methyl group and methyl group. What are the possible geometrical isomers? In cyclic systems, you better to avoid applying formula. Sometimes we are getting wrong answer when the cyclic compounds are what given. Just by applying simple logical methods, we calculate total number of geometrical isomers. Now this is my first example. How to write geometrical isomers according to the given molecule. Okay, 3-membered ring system is given, and how many methyl groups are there? 2 methyl groups are there on adjacent carbon atoms. Okay, 2 methyl groups on adjacent carbon atoms. Fine. How to arrange these methyl groups? I am taking like this. One time I am taking 2 methyl groups same side. Methyl and methyl same side. Methyl and methyl same side. Next one here, 1 methyl above the plane and 1 methyl below the plane. Okay, actually this one is taken as cis form and this one trans form, cis and trans. Totally how many geometrical isomers? Number of geometrical isomers equals to 2. Number of geometrical isomers equals to 2. These are the geometrical isomers of 1, 2 dimethyl cyclopropane. 1, 2, 1, 2, 1, 2 dimethyl, 1, 2 dimethyl cyclopropane. 1, 2 dimethyl cyclopropane. 1, 2 dimethyl cyclopropane. Yes, it is visible, no problem. 1, 2 dimethyl cyclopropane. Come to next example. Here I am going to give a 4-member ring system. Yes, like this, methyl and methyl. Write possible geometrical isomers of this molecule. 1, 2 dimethyl cyclobutane. So in 1, 2 dimethyl cyclobutane, again same thing. One time both methyl groups we are taking same side, that is above the plane. Here also same thing, above the plane. Now this one cis form. Next one here, methyl above the plane and this methyl below the plane, and this is trans form. These are the 2 geometrical isomers. Number of geometrical isomers equals to 2. Just by doing practice you will get idea, no problem. Don't apply formula in cyclic compounds. For example, if your molecule is completely symmetrical, so directly you can apply 2 to the power of n formula. But sometimes in cyclic compounds like this, now better to avoid applying formula. Just on logical approach you write cis and trans form. For example, one more question I am giving that. Same 3-member ring system like this. 3-member ring system. Methyl groups are given like this. 1, 2, 3 position methyl groups are there. Then how to write geometrical isomers? Just I am writing the possibilities. 3-member ring system. Again here also 3-member ring system. And how I am going to arrange methyl groups. You observe this one. In first case I am taking all methyl groups above the plane. Like this. All methyl groups above the plane. Here methyl. Next one CH3. Again CH3. Okay. All methyl groups above the plane. You can take either above the plane or below the plane, no problem. Once the symmetrical substitution is given, either all groups are above the plane or all groups are below the plane, both one are same, no difference. Next, in the second structure, just I am trying to change one methyl group like this. Now methyl and methyl, these two methyl groups are above the plane and one methyl I am changing to below the plane. Is it clear? That is the second possibility. So more than that, there is no chance. That's why what are the number of geometrical isomers? Number of geometrical isomers equals to 2. Very simple question. Total number of geometrical isomers equals to 2. Okay. Another very important example. I am trying to discuss all special cases. For example, 4-member ring system given. 4-member ring system. Methyl, 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 methyl. Write all possible geometrical isomers of this given molecule. 1, 2, 3, 4 tetramethyl cyclobutane. Okay. So how to arrange now methyl groups on the given 4-member ring system? Just I am taking like this. Diagonally I am writing the bonds. Yeah. Yeah, yellow is better, right? Arrange the 4 methyl groups. First one given molecule is symmetrical molecule, okay? Yes. Substitution is given very symmetrical. Just I am trying to write all methyl groups above the plane. This is the first possibility. All methyl groups above the plane. Next, what I am doing in the second molecule, I am taking 3 methyl groups above the plane. Just I am trying to change one methyl group orientation. I am taking like this. In the first case, what I am doing, all methyl groups above. Here, just I am taking one methyl below. What is the another possibility? In another possibility, I am taking like this. I am not changing position of these methyls. I am selecting 1, 2 position, 1, 2 position, methyl below and methyl below. That is also another possibility. Here what I am doing, 1, 2 position below, 1, 2 position below. Okay, right. In the next one I am taking 1, 3 position below and these two as it is from the first structure. Okay, right. This is the another possibility. So these are the maximum possibilities. Now you remember this point, you may get some doubt here. Sir, actually here all methyl groups are above the plane, just like above. Is it possible to take all methyls below? Yes, you can take, no problem. All methyls below. Either all methyls above or all methyls below, structure should be same, no problem. That's why we are taking now similar symmetry structures, all above or all below. You select any one only. Okay, right. So what are the total number of geometrical isomers? Number of geometrical isomers equals to 4. Very good example. Number of geometrical isomers equals to 4. Okay, next one. Another example. For example, 6-membered ring is given. 6-membered ring is given. 1, 2, 3, 4, 5, 6. Very important example. How to write all possible geometrical isomers of the given molecule. At each carbon atom, 1 methyl group is there. Okay. To represent all types of geometrical isomers. Now remember these examples. These are very important in optical isomerism also. But there on the basis of symmetry elements, we are explaining the optical activity. Same type of molecules we use in optical isomerism. Yes. What is the arrangement of groups on 6-member ring system? Totally here 6 methyl groups are there. I am taking like this. All methyls above the plane. Like this. thick wedge nothing but above the plane. All methyls above the plane. This is one possibility. Not only this one, you can take all methyls below the plane. Both one are same. Either you can take all are above the plane, all are below the plane. What is the second possibility? Here I am taking one methyl below the plane and remaining all methyls above the plane. Is it possible to write this one? Yes. This is the second possibility. Okay, right. And come to third one. This below the plane group you can take at any carbon atom, all are equivalent. Okay. Next one, here I am taking 1 2 position below the plane, 1 2 position below the plane and all methyls above the plane. Clear? At 1 2 position I am taking methyl groups below the plane and at remaining carbon atoms all are above the plane. Next one, we can also arrange like this. Not only 1 2 position, we can also take at 1 3 position. Not only 1 3 position, we can also take at 1 4 position. Okay. Arrangement of methyl groups. Next, at remaining carbon atoms above the plane, above the plane, above the plane and above the plane. Here also same thing. Above the plane, above the plane, again above the plane. This is one possibility. Come to another one. Here three groups I am taking below the plane. One time at 1 2 3 position by using what? Broken wedge. 1 2 3 position. Another possibility 1 2 4 position. This is also possible. Okay. And 1 3 5 position. 1 3 5 position. 1 3 5 position. Okay. And at remaining carbon atoms you can arrange methyl groups like this: above the plane, above the plane, again above the plane, CH3. Okay. Next one here, above the plane, methyl, methyl, methyl. So no need to write that methyl group. Why? Because by default that should be what? Methyl, if nothing is given. No problem. Right. Next one, above the plane, methyl, above the plane, methyl, above the plane, methyl. What are the total number of geometrical isomers? Very important example, special case. Number of geometrical isomers equals to 8. Total number of geometrical isomers equals to 8. Very, very important example. Okay, right. Let me check once again. All methyls above 1 2 1 3 1 4 1 2 3. Yeah, correct. Let us go to next example. This is previous question. Molecule is given like this. Yeah, COOH, opposite direction COOH. Here phenyl group is given. Phenyl group is given. This is previous question, PYQs. What is the name of this molecule? Truxilic acid. Truxilic acid. What are the possible geometrical isomers of this truxilic acid? Now I am going to take now 4 membered rings like this. Clear? These are the molecules. Then try to arrange corresponding groups. First I am taking here phenyl above the plane, COOH above, again here COOH above, this phenyl also above. This is my first possible arrangement. According to the given molecule, just I am taking all 4 groups above. All 4 groups above. Okay, right. Next one carboxylic acid, just I am taking down. We have phenyl as well as carboxylic acid. Okay, first you try with carboxylic acid. and remaining pH, COOH and phenyl. This is the second possible arrangement. And what is the third possible arrangement? In third possibility, I am taking phenyl below, and this, one second. So from the first structure, I am taking phenyl down and remaining groups are above. COOH, phenyl and again COOH. Now this is the third possibility. Next one, I am taking two groups below. Just like I am taking from 1 to position carboxylic acid and phenyl. From 1 to position I am taking below, and here as it is carboxylic acid and phenyl. This is the fourth possibility. And what is another possibility? Instead of 1 2 position, you can take 1 4 position. Here COOH below, again COOH below. Next phenyl above, and this phenyl also above. These are the maximum possible varieties. Now you can also try different types of possible arrangements by using what same molecule, but these are the maximum possible arrangements. What we are doing here, all groups above, you have two different groups but in opposite direction given, phenyl, phenyl, COOH and COOH. Okay, either you try with carboxylic acid or phenyl, whatever it may be, but in the first one you can take all groups either above or below. In the second one, I am trying with carboxylic acid. I am trying to keep that carboxylic acid below. Fine. But from the second molecule, from the second molecule to write third molecule, I am taking option from phenyl. Phenyl below, remaining all are above. In this molecule, instead of taking one group, I am selecting two groups from 1 2 position. COOH and phenyl I am keeping down. Next one, I am selecting COOH and COOH down. So these are the maximum possibilities. What are the total number of geometrical isomers? Total number of geometrical isomers equals to number of geometrical isomers equals to 5. These are the total number of geometrical isomers. This is a very good question. PYQs. From PYQs, I selected this question. Truxilic acid, total number of geometrical isomers equals to 5. Okay, right. Next one, another simple example. Actually, a lot of varieties are there. One more simple example I am giving, that 6-member ring system. Methyl groups are given like this: methyl, methyl, and methyl. Just you write possible geometrical isomers. Already this type of question given by using 3-member ring system. Similar to that one, you write geometrical isomers of this given molecule. Right? 6-membered ring system. Again 6-member ring system. Okay. Here first I am taking all methyl above the plane, above the plane, above the plane, again above the plane. Next one, in the second example, two methyl groups I am taking above the plane and one methyl group below the plane. What are the total number of geometrical isomers? Number of geometrical isomers equals to 2. Very simple example. Okay, why? Because some more complicated examples are there that we will discuss in the next class. Almost in the next class I will finish geometrical isomerism. So before going to that, just I am giving one simple example. At 135 position, 135 position, identical groups are given. Now that is the way of writing geometrical isomers. I am not giving any cis transform, just arrangements I am giving. Okay, right. Clear? Okay, no problem. This example is enough in this class. In the next lecture, we will discuss some other varieties of geometrical isomerism. Those are also very important for mains and advanced. Okay, thank you.